this is a talk where I try to bring, well, really it's a span of some topics in algebraic topology, all the way back from the 50s to now, really present day. But obviously I can only touch on certain things, but there's a common theme. The first thing, there we are. The first thing is I want to talk about manifolds. Manifolds are really quite a central theme in topology geometry. And let me start off with saying what a manifold is. A manifold is a topological space, and locally it looks like Euclidean space. So given a point, a green point around it, I find a small neighborhood that is in one-to-one correspondence to Euclidean space R to the D. And generally I want this correspondence, you know, R to the D, I know what a smooth function is on there, and so I should be able to say what a smooth function might be on the manifold. And those are the sort of manifolds I want to look at, where I can make sense of smoothness. And of course, if my manifold has a boundary then, and the point is on the boundary, then of course I can only find a local neighborhood that looks sort of like upper half space, like this. So fundamental question then is really, can we classify all the compact manifolds, say without boundary for now? Because once I know things without boundary, I can also understand them with boundary. So this is an absolute fundamental question. It's sort of like also asking, you know, how many groups are there on you know, with 6 elements, and the same sort of classification question you can ask for compact manifolds. So compactness here is just to give us some sort of finiteness notion. The first thing I want to note, it becomes actually quite an important thing to note, is that the empty set is a manifold of any dimension. Why? Well, the definition of a manifold is for all elements in the manifold, there exists a neighborhood which looks like R to the D. But of course, for any statement for all, if the set is empty, that you take it over, then of course that's trivially satisfied. That's slightly technical answer, but it's really convenient to have the empty manifold considered as a manifold of any dimension. Okay, so let's just look at what it might mean in for different D. So if D is 0, so we only have really points, then the compactness condition just means we have finitely many points. And that's simple enough. If we have, on the other hand, a dimension equal to 1, well, if anything locally has to look like a little line, then of course, if I continue and it's supposed to be compact, then I come back to myself, and really I just describe a circle. And again, the overall compactness means that I can have at most finitely many such components. So that's easy enough. And finally, in dimension 2, we also have a complete classification. And when I say classification here, I just mean, you know, they're one-to-one maps, up to one-to-one maps, either homeomorphisms or diffeomorphisms, as I said before. So here, the classification is, well, first of all, we distinguish between those manifolds or surfaces that are two-sided, like the sphere, the torus, and the double torus, or like the Klein bottle here, which really has only one side. So these are the orientable ones, and as a Klein bottle and things like it are non-orientable. And the claim here is that actually we do know a complete classification, namely all these compact surfaces that we know are either of the form oriented case where I have basically tori stuck together like this, and more and more and more. And depending on how many of these holes I have, that's my genus. So this is F1, this is F2. Or in the non-oriented case, it is a matter of they're similarly classified and given by Klein bottles and higher genus version of that. I should have really started with RP2, so projective plane, and sticking many of those together, I get an NG. So it's completely classified, and you might try to ask yourself, how does one possibly, if I have something, if I have a surface, how do I know, how do I tell quickly which one I'm actually dealing with? It might not be presented so nicely as here, but rather more complicated, and maybe I only have local information. For example, the surface might just be given in small polygons glued together on along edges. And here's something that goes back to Euler, really. He introduced what is known as the Euler characteristic. So if I start with a surface, which is divided up to polygons, then the Euler characteristic is defined as the number of vertices, V, minus the number of edges, E, plus the number of faces, okay? And that's just a number. And surprisingly, for surfaces, this number tells us everything we need to know. Apart, we need to also know whether it's oriented or non-oriented, but that's all. And let me just go on a little bit on this Euler characteristic. So here's a nice stamp from, depicts Euler, which is rather nice. And here you see the polyhedron, and you can count how many triangles it has, how many edges, and how many vertices. And you do exactly this formula. Sorry, this is in German, Ecken, Kanten, and Flächen. And what you get is the number 2. And the beautiful thing is that it doesn't matter if you start off with any polyhedron and you do this calculation, you're always going to get 2, or start with this sphere and cut it up into polygons. Again, do the same calculation, it's always 2. So it's not so easy actually to prove rigorously that that is the case, but that a beginner's course in algebraic geometry, algebraic topology should be able to prove that. Okay, so here are some examples. How can we construct surfaces? Indeed, it turns out that every surface can be just constructed out of a polygon where I identify the edges according to some prescribed pattern. So here I start with a rectangle, and what I do is I identify the bottom and the top edge. And of course, if I do that, then I get a tube, and then I glue this circles at the ends of the tube together as well, this one and this one, which will be circles. And then I get a torus. So and therefore the Euler characteristic of the torus is, well, once I glue everything together, this vertex is identified with this one, and this one. So I only have one vertex, and I have 2 sides really, namely this one identified with this, and this one identified with this. So 2 edges, and then I have plus 1 face, namely the one polygon, one rectangle. So the Euler characteristic of the torus turns out to be 0. And similarly, as a Klein bottle, you can be built out of, well, again, 2 top and bottom of the rectangle identified to give a tube, but then the sides are slightly differently identified. And of course, that's very difficult to do in R3, but abstractly we can do that. In this case, of course, the calculation comes out to be exactly the same, also to be 0. So here we see the Euler characteristic doesn't quite distinguish between these two. I need to know that this one, the torus, is orientable and the Klein-Bottle is non-orientable. Okay, now what about for the other surfaces? There's actually a very nice gluing formula. And so this might look a bit specific now, we come back to it later. Namely, the gluing formula tells me how, given one surface S1 here with a boundary and another one also with a boundary circle, so S1 and S2 are tori, each of which have a deleted disk, so have boundary, and I glue them together over S0, namely their common circle here. And the formula, the Euler characteristic formula, is just given by the Euler characteristic of the two surfaces, S1 and S2, minus the one where I identify them. And that's clear why this need to be done, because I need to take this out, the edges and the vertices here would otherwise be double counted. And so this is actually the right gluing formula. And if we look at what it gives us in this case, so this is my genus 2 surface, F2. I build it out of a genus 1 surface with one disk removed. One disk is basically one face removed. So the Euler characteristic of that is one less than I started off with. And then I have another torus with one disk removed. And then I have to subtract, according to this formula here, as the Euler characteristic of the circle, which of course is 0. Here I can represent the Euler, the circle as a triangle, 3 vertices, 3 edges. That's 3 minus 3 is 0. So altogether I get a -2. And similarly, higher genus, I can now repeat this and I compute the Euler characteristic of a higher genus, and I can see that the Euler characteristic determines the genus and vice versa. And indeed, the complete classification gives us the Euler characteristics of Fg as 2 minus 2g. And in the non-oriented case, I get a similar formula, namely 2 minus g. And that's completely describing now, classifying my surfaces. So this way we see that somehow algebraic topology, simple invariants, can help us actually identify and classify manifolds. That's up to dimension 2. And then we might want to go higher. Now that's a completely different question. Dimension 3, recently, well, 15, 20 years ago now, with Perlman's solution of the Poincare conjecture, and Ian Eigel later on has some further results in 3-manifold theory. We sort of understand 3 manifolds now. 4 dimensions are completely beyond our understanding, and somehow dimension 5 and higher become a little bit more easy again. However, even if we had a classification, and indeed it's not quite possible to have a complete classification in the higher dimension, but even if we had it, we still would want to know what about the maps between these different manifolds, or indeed what about the automorphisms of a given manifold. And that's quite an important thing, because somehow in mathematics, unless you don't understand really an object unless you understand its symmetries, and that's sort of the idea behind. And of course, if I just very quickly go back, for points for dimension 0, we do understand it because it's just a symmetric group on, in this case, 10 points of 10 letters. So that's completely fine. We have a good grip on that. But here it's already more complicated. What are the diffeomorphism of the circle? If they're orientation preserving, then actually it's a complicated group. However, up to homotopy, certain flabbiness, really, essentially, the only thing I can do is really rotate the circle around. And those are effectively all the interesting, that's a whole space, representing the whole space of interesting diffeomorphisms. That's a theorem. But in dimension 2, things have been very difficult, and indeed it's a topic by itself to understand that. The mapping class group of surfaces comes in. Okay, so now I have set up really the problem. It's really quite a fundamental problem. And as I said, in that higher dimension, because effectively there's something called the fundamental group, and every group can occur of higher dimensions, and groups they're basically unclassifiable if I don't restrict myself to certain things. So I'm going to be in trouble if I want to just classify manifolds straight out. So in the 50s, there was a notion that seemed to be a nice equivalence relation on manifold, and we can therefore study something up to this equivalence and try to understand manifolds relative to that. So this cobordism notion is quite easy and a rather beautiful thing. Namely, I say M0, so that's the boundary here of the surface I'm looking at. So W is this whole thing, M0 is the boundary here, and M1 is the boundary here. And I say M0 and M1 are cobordant if there are the boundaries of a manifold one dimension higher, which is W. So I want to find a W so that W's boundary is M0 union M1, and then M0 and M1 are defined to be cobordant. Now, I should really check this is an equivalence relation, right? First of all, is this a reflexive relation? Say, is M0 equivalent cobordant to itself? But yes, if I just take M0 cross the unit interval, then I basically get a fat tube. On both sides of the tube, I have M0 as the boundary, and so M0 is cobordant to M0. Is it reflexive? Is it symmetric? Yes, of course, because M0 and M1 are still the boundary of W, even if I think of it as M1 union M0. So that's obviously correct. And indeed, transitivity also holds, because if I have, say, an M1 and another M2 with some other cobordism, then I can glue the other cobordism to this given one along M1 and see that M0 is cobordant to M2. So it's an equivalence relation, and it cuts down quite significant. Indeed, here are the first equivalent sets. So I'm distinguishing here between orientable and non-orientable. So that just means that when I look at the W, the sort of W's I allow in the oriented case, I would only allow oriented ones, and in the unoriented, I can have anything. So if I'm thinking of manifolds in the oriented case, then in dimension 0, points will come with an orientation. They're either positive or negative. And an interval like this one, which has an orientation, will start with a point that's negative and end with a point that's positively oriented. So if I have just a bunch of positive and negative points, these cobordisms would basically say these 2 points I can ignore because they are cobordant and to the empty manifold. And so really this equivalence class just records sort of the surplus of pluses or minuses that I have. And so really this is equivalent to the set Z. On the other hand, if I start with manifolds of dimension 1, so just a bunch of circles, then clearly all of these manifolds can be just thought of the boundary of a sphere where I just punched in a number of holes. So again, any number of circles is cobordant to the empty manifold here. So really, I only have one element in this cobordism class. And finally, when I look at oriented surfaces are, these higher, here's a genus 2 surface, but I can have more higher genus or spheres and tori. But the particular feature, of course, because I can embed them in R3, is that they bound sort of the interior. And if I fill it in like a solid donut, then the surface, which is the torus, is just the boundary of the solid donut. And similar with these higher genus surfaces. So again, really, all the oriented surfaces are boundaries and therefore cobordant to the empty manifold. Let's just do this exercise also in the non-oriented case. Well, in the non-oriented case, I still have intervals that will basically cut off for me or equate 2 points to 0. And so what I'm left is actually just the parity of number of points that I started off with. So I'm getting a Z mod 2. Well, this is the same relation for unoriented or non-oriented. The surface is always, the sphere is always going, with number of holes is always going to be a cobordism between a number of circles to the empty manifold. Oops, that should not have a plus. And in the surfaces, we can actually, requires a little bit more thought and proof, but the cobordism group there is, again, just either oriented or non-oriented. So the Klein bottle, for example, is not, sorry, did I say that correct? I don't want to do Klein bottle, sorry. I want to say the projective plane is not cobordant to the empty set. So we get just 2 elements. Now this, as you see, cuts down our set of manifolds into very rough classes, but it's a very interesting relation nevertheless. And I'll come back to that in a little bit. So here's something from the 50s, namely, sorry, let me go back. So we have these cobordism classes, but actually we have much more structure on these cobordism classes. Namely, in dimension D, if I fix D, these cobordism classes actually form an abelian group. Namely, I can just take the disjoint union of manifolds, and that will be my addition. And the 0 element is just the empty set under this operation, of course. And it's yeah, and the the negative, the inverse of any manifold is actually just the same manifold with the opposite orientation. And then I think of it, the cylinder that gave me before the reflective relation, I can now bend it around, and I can see this gives me sort of the cobordism between the manifold twice, but with in opposite orientation. Now the rings, there's a lot on ring structure. If I take all of these classes together, and the ring structure then is Cartesian product, and the unit is just the single point. And we call this now, this whole thing is actually a graded ring structure. Now, surprisingly, this is what Tom was able to prove in the 50s and got his Fields Medal for that, is that this group here, I can interpret as the homotopy groups. I say that in what I mean in a moment. The homotopy groups, an algebraic topological invariant of a certain space. Now this looks like a scary space, but it's not. I'll say something in a moment as well. It's not too bad, something we can understand. So really, so what are the homotopy groups of a space X? I look at maps from a D sphere into my X, so sort of look for holes of in X that are dimension D. They're all pointed, meaning there's a base point here going to a base point there, and then I look at the connected components. So those of you who are maybe familiar with homology, this is another way of trying to find the d-dimensional holes in my space X. Okay, that's just a refined version of that. And then Tom actually proved, having identified this, and as I say, the space is actually something one can compute with and rationally, ignoring torsion. This ring here, taking everything together, all the manifolds in the oriented case, turns out to be just a polynomial ring. Polynomial ring on different indeterminants xi, where actually, an element here should be represented by a manifold. And so these xi can be represented by complex projective planes. So CP2 is a space of lines in C3. And so it's a complex two-dimensional manifold, and it's the lines in C3. And here, this is the lines in C5, and so on. So very explicit computation. Okay. Now, it's a bit, one should really try to understand maybe a little bit how can a manifold, say any of these, how can it give rise to something that looks like a map into some space, this space here. How can we possibly find that? And I think this is a beautiful construction, the Tom collapse map, which I think is these days probably not taught often enough. So we start off with a manifold, say M, which is embedded in some large Euclidean space. So the dimension of M is D, and we think of N being very large. Okay, so here, this is the dark line, that's my manifold. But then, I take a little tube around this manifold, and then I get what's this slightly stripy area. And then I ask myself, well, then I can construct a map from anything in here, D plus N. I take say a point here, this point here, that's my B, and I think of it as something on the surface, the nearby point, and something that is perpendicular to the tangent bundle here. Okay, so it's X plus this vector T. And this point here, represented by x and t, I map into this plane, which is perpendicular to the manifold through x, and I remember this vector t. That's all I do. I just remember the perpendicular plane here and this vector. And that defines for me a beautiful map from the one-point compactification of the Euclidean space, which is just a sphere, into something, well, it's just reformalizing what I get here, namely, what do I really have? This plane here is an n plane in r to the d plus n, and I have something, the t is really an element in that plane. And that's really this universal n-dimensional bundle over the Grassmannian, that should be a plus, the Grassmannian of oriented n-planes in R d plus n. And so really that's what I get. So I get a map from Sn into this one-point compactification of this universal n-dimensional bundle. And I let n now go to infinity and k as well. And that defines for me this space that appeared in Thom's theorem. So it's just by this construction that's really tells me really everything and package it. Okay, so here's a picture of René Thom. As I said, he got Fields Medal in the 50s, 58, I think. And that sort of nearly completed the story of cobordism at the time. Then cobordism appeared in a completely different setting, and namely in topological quantum field theory. So if I lost you before, this is a moment to tune in again, because we sort of start at the beginning again. Okay, so topological quantum field theory, we start also with the same picture really, also the cobordisms, only that I'm now thinking of M0 here as a source, my cobordism W as a map, and M1 as a target. So for those of you who are familiar, this is I'm building up a category, the cobordism category. So I think of these as arrows, these cobordisms. Now, where does this come from, and why the title, and why does it have strings in them? Well, Witten, I just take this picture, I don't know what exactly he was talking about, but in particle physics, you talk about points moving in space, and then they might collide and have interactions with other particles and so on. In string theory, what you want to do is replace your point particles and their paths with little strings. And so the path now is not just a line, but actually a tube. And as different particles interact, you get complicated surfaces. That's sort of the idea. And Tia, listening to Witten and indeed also to Graham Siegel, really, who constructed conformal theory, defined something that we now call topological field theory. Namely, we look at this setting, we look at our strings in this case, we look how they move with time, and then at some other time one, we have another manifold, and then it might move on again, and we at another time 2, we have M2. And of course, we want to understand how things develop. Strings might have some information associated to them, and that information changes as we move through time to the target M2. So mathematically, we formalize this in what we call it TQFT, topological quantum field theory. Namely, we associate to every d-1 dimensional manifold a vector space, and to every d manifold, so W1, we associate a linear map. So we go from the vector space associated to M0 to the vector space associated to M1. And of course, as we move from one to the next, we want, of course, the rule that if I stop and then assign a new map, then the whole linear map should be the composition that's expressed here, right? So if I glue one cobordism to another, then the linear map associated to that should just be the composition of the two linear maps associated to each of the cobordism W1 and W2. And then further, I have one more condition, because disjoint union of manifolds is, of course, an important operation. And under my association, the topological quantum field theory F, I want disjoint union to go to tensor product of vector spaces. So F is now what we call really a functor from the category of manifolds to the category of vector spaces, but maybe that's not so helpful. The point is, because I take tensor products to, disjoint union to tensor products, that means the unit of disjoint union, which is the empty set, has to go to the unit for tensor product, which is just the ground ring, C, in our case. Okay, so that's just a little observation. And then we can try to understand what this does in dimension 2, since we understand a little bit dimension 2, and dimension 2 is not completely trivial. So here's the folk theorem, namely in dimension 2. Well, the first thing we say, okay, to S1, which is one-dimensional, we have to associate a vector field, that's a vector space, let's call that A. And disjoint union of different S1s has to go to tensor product. So I get a tensor N. And then I have linear maps. So for this pairs of pans, I get a map, linear map from A tensor A to A. For this bent over cylinder, I get a map from A tensor A to what I associate to the empty set, which was the ground ring C. And this more complicated thing, because I didn't emphasize that enough, the point is that the linear maps that I associate, they're only dependent on the topology. Okay, so that means since the topology of this is the same as of the straight cylinder, really and here I basically just get the identity associated. What I get is what's sometimes called Frobenius algebra. For me, a Frobenius algebra is something that satisfies all these things and has all these things. And indeed, it turns out any such algebra satisfying any finite dimensional Frobenius algebra gives rise actually to such a functor. And the finiteness condition is very much a consequence of this snake here. Okay, so that's just giving us a little bit of a feeling maybe for what a topological field theory might do. Why was Atiyah interested in these things? Well, he also was interested in the question that I started off with, namely to classify compact smooth manifolds. And indeed, these topological field theories give rise to an invariant like the Euler characteristic. And so let me try to explain how that works. If we have a d-dimensional manifold, which doesn't have any boundary, so boundary is empty. We can think of it, of course, as a cobordism from the empty set to the empty set. So a TQFT will associate to this d-dimensional manifold a linear map from what I associated to the empty set C to C. And that, of course, can only be a constant, an element in C itself. And that is our topological invariant, because remember, the idea was that the topological quantum field theory should only depend on the topology of the underlying, the linear map should only depend on the topology of the underlying manifold. Okay, so that was his interest. So we might just about see how our Euler characteristic fits into this scheme. And indeed, here's an example. We can associate to all d-1 dimensional manifolds just the ground field C, defining F, and then to any cobordism W, I assign the exponential 2 pi I, and then this formula in terms of the Euler characteristic. Namely, I take the Euler characteristic of the source manifold, the Euler characteristic of the cobordism, minus the Euler characteristic of the target manifold. And remember, we had our gluing formula, which I showed you in for surfaces. That gluing formula also holds, and I challenge you to prove it in higher dimension. And that is exactly the relation that you need to prove now that this is really a functor. In other words, that if I compose the map associated to W with the map associated to W2, then I get the map that I would associate to the glued surface or cobordism. So this is a nice example. But then there was a question a little bit in the direction of, well, can we understand all such topological field theory? In the sense that we understood all topological field theory in dimension 2. Can we do this in generality? And so, somewhat surprisingly, but maybe not actually that uncommon in mathematics, the answer is much easier, or the problem is much easier when you state it more complicated. You make the problem more complicated, but you can answer the question more easily. So here, the more complex problem you're studying is actually that you say, well, I don't just take manifolds, the d-1 dimensional manifold, that's fine, but I don't just take one representative of my topological, of my diffeomorphism class, W, but I take loads and loads of different ones, and indeed the map might differ just a little bit between these. So in other words, I'm enriching my category, namely, I take my manifold W1 and W2, M1, sorry, M0 and M1, and I look at W's that are cobordism between them, but I'm not just looking at this one, but I can move this up and down, I punch it, and I have this whole moduli space of surfaces that fit in these boundary conditions. And this is a space of all these W's that fit in between, which are now my morphism space. So this is this M for moduli, and later on we might think of it also as the classifying space of the diffeomorphism group of the W's. So this is a much bigger category, which looks at first much more complicated. But actually, we were able to prove something. So as I said, this is a category which morphism spaces. And one way a topologist, especially a homotopist like myself, studying a category consists of objects and maps between them, is to associate to it what we call the nerve or the classifying space, BC. And how do I do that? Well, for every object in my category, I take a point. So maybe for every D-1 manifold previously, I take a point. And for every morphism, so D cobordism, I take an interval. And of course, this point is glued to this point, and objects are glued to the corners. Now, if I see then a triangle like this one, where I have two composable maps, F and G, and of course, I have another interval for the composition, in this situation, I just fill in the whole triangle as well. And I build up higher and higher dimensional tetrahedrons and simplices for higher and higher composable sequences of maps. And that gives me a nice space. And that's an interesting space to have. It tells me quite a bit of about the category. And indeed, we were able to compute what we get when we do this procedure to this enriched cobordism category. And somewhat surprisingly, you get more or less the space that we started off with, that Tom looked at. This, this omega infinity MTSOD, only that we get one of these spaces for every fixed D. Okay. Namely, instead of looking at just the universal bundle over the Grassmannian, I now take its orthogonal complement, and I just look again as before, maps from the sphere into it. And indeed, again, the Tom collapse maps plays an important role here, with a tiny twist, namely, to this point here up there, I'm not just defined by the point X on the manifold and this vertical vector T. I don't associate the normal vector space, but I actually associate the tangent vector space and T. And that's the only difference. And it's a beautiful map that helps us to prove actually this theorem here. Okay, so tiny twist. Okay, so we came back in a circle. The beautiful thing again here is that indeed this space, as before with Tom, we can compute it. We can compute its homology or homotopy rationally completely. Here's a formula for it. And indeed, if we just look at dimension 2, we get this beautiful formula for the cohomology of the space. So it's a way of counting it once the holes in this space here, this moduli space. And it's just a polynomial ring again on indeterminants of degree 2i. So kappa 2 has dimension degree 4. And not only can we do this for surfaces, that's a solution of the Mumford conjecture by Madsen and Weiss, but in higher dimension, this has been achieved by Galasius and Randall Williams, and for even dimension and odd dimension, there are many results by Budwinnik and Perlmutter. I can't go into all the details. There's a whole big topic out there. One of the revolutions, I think, in the last 10 years in algebraic topology of manifolds. Just to finish off, let me just come back to what does this actually maybe tell us about strings and string theory? Have we gotten any closer? Have we made any progress? So here we sort of have the cohomology of this space, something that I haven't quite explained. That space here, you remember that was a classifying space of the cobordism category, and the morphism spaces of the cobordism category had something to do with the classifying space of the diffeomorphism of the underlying manifolds. And that's the part we are now catching. So maybe just a very quick go back here. So this space here is the space of paths when you do string theory, right? You start off with some strings and you develop it over time, and you end up with some other number of strings here. And you might want to understand how whatever properties you have associated to these strings changed when you come over here. And in the Feynman integral formulation of particle physics, you do exactly this, only that, of course, you have here points and end up with points, and in between you just have path. And the Feynman path integral is somehow integrating all the potential ways of ending up over the different paths, and therefore gives you a sort of an prediction of what you might end up later on. Now, in string theory, you would have to integrate over this space here of all the different surfaces, if you like, this moduli space of surfaces, or this big space here. Now, these are infinite dimensional, and integration over infinite dimensional spaces, normally, it's very hard and nearly impossible to make sense of that. However, the topology of those spaces is crucial to that integration. And here we effectively understand the topologies, we understand the holes now of that space a lot better. And let me just finish up with something you again know, trying to drive home my point. Namely, once you understand the holes, you can do the integral computation. And that's, of course, something that you are familiar with just computations of residues, right? If you look at the integral, the line integral of 1 over z, the only thing you need to know whether you are catching the origin, in this case, the singularity. So the domain actually consists of C without 0. So in other words, the whole here is extremely important. And then you pick up a factor of 2 pi I. Or when your circle doesn't contain that singularity, of course, you have no problem with it at all. So all in all, I think I should finish here just saying that it's somehow very surprising. It has been wonderful to be part of this story where you start with cobordisms in the 50s and suddenly these coming up in a completely different field, namely topological quantum field theories, and actually finally coming together, and maybe not surprisingly coming together, giving us these moduli spaces and answers and computations of those. So thank you very much.